So today we'll be graphing an ACF problem that has to do with airplanes flying. So in this problem it says, due to a large volume of incoming flights, an airplane is asked to stay within a holding pattern near LAX. The holding pattern is the flight path maintained by an aircraft awaiting permission to land. At 7.25 minutes after entering the holding pattern, the plane's minimum distance from the airport is 80 miles. So we're going to make a note of that. At 7.25 minutes, the plane's minimum distance is 80 miles. That's the minimum. And then the plane's maximum distance from the airport is 220 miles, 12.08 minutes after entering the holding pattern. And then for the maximum distance, it is 12.08 minutes, where the plane is at 220 miles from the airport. Maximum. And then from these given points, we can determine a sine function. So yeah. So the first thing we're going to look for is the amplitude. The amplitude in which the maximum y minus the minimum y is divided by 2. So from this equation, from these points, we can see that the max y is 220 minus the minimum, which is 80, divided by 2, is equal to 140 over 2, which is equal to 70 as the amplitude. And then the next thing we're looking for is the vertical shift, in which for the vertical shift you take the maximum y value plus the minimum y value divided by 2. So instead of subtracting, we add it. So 220 plus 80 over 2, which is equal to 300 over 2, which equals to the vertical shift to be 150. Now the next thing we're looking for is the period. For the period, we're going to have to use 2 consecutive maxes or mins. So for the period, from this one, I use an equation in which 2 times the maximum x minus the minimum x. So from here, we can use 2 times the maximum x, which is 12.08 minutes, minus 7.25 minutes, which is equal to 9.66 minutes as the period. And then for the next one, for the phase shift, we can use the minimum minutes, 7.25 for the phase shift, and then keep subtracting, and then we can keep subtracting the difference between the maximum and the minimum. So in which we use the 7.25 minus the difference between 12.08 minutes and 7.25 minutes is 4.83, which leaves us to 2.42 minutes as the phase shift. And then we can't subtract anymore, or else it would be a negative, in which time cannot be negative, so we just keep that one as there. And then the next one is to graph it. Before we start graphing, we are going to have to make a sine function, so then we know how to plot our points. So the first one would be over here on the white paper. y equals, and then we use the amplitude that we found, which was 70, times the sine, open the parentheses, in which you put the 2 pi over the period, and the period is 9.66, and then the phase shift x minus, which we got was 2.42, and then you add the vertical shift, which is plus 150, and then from there we can start graphing. So next we graph it using a straight edge, and then also using the maximum and minimum in order to find the points we can use for the y-axis. So I already counted this ahead of time, so we just outline this in black. Okay. Then from there we can start labeling our axes. So over here we would have time in minutes. And then over here on the y-axis we would have the distance in miles. And then from there we can start numbering our axes. So for the y-axis I decided to go up by 50, since the maximum point is 220, so might as well. And then for the minimum, for the x-axis, I chose to go up by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18. And then from there we can start plotting our points. So first, our points, we were already given the minimum, which is 7.2580, and then we were given the maximum, which is 12.08220. However, in order to graph the sine equation more accurately, we would have to find more points going from the change up or down. So the change from 7.25 to 12.08 is actually 4.83 minutes. So from here to here is 4.83 minutes. And then if we keep on going, we'll eventually hit 16.91 minutes, and then have the minimum, which is 80. And then if we go in this direction, we would eventually go to 2.42 with the maximum of 220. And then from there, we start graphing the points. Eventually, it'll start to look more like a sine equation. So now we can start plotting our points. So we have 2.42, 220. So 2.42, 220 right here. The next one would be 7.2580. So 7.2580 here. And then we would have 12.08, 220, which is around here. And then the next one would be 16.9180, which is here. And then from there we can start graphing it. And then we can keep going right here. And then that's how we graph it. And then for the next part, part B, it asks us to find a time in which between 0 to 20 minutes, when does the distance of the airplane hit 100 miles from the airport? So if we set it up, we write down first we have to graph this equation, our given equation, which is y equals 70 sine, like before. 9.66 period, x minus 2, 150. And then we would also have to graph y equals 100. And then we would have to find the intersecting points. So this, it will eventually look like this. And then we have to find the intersecting points in which when y equals 100. And then in these points, it's given the answers. So I'll be graphing this on Desmos and I'll be showing you. So before I started graphing these equations, I set up my window to be for the x-axis from 0 to 20, so then it would be easier for me to see when it intersects. So then we start graphing our equation that we found here. And then we also graph y equals 100 to find out where it intersects. And then from here we find that on these points right here from 0 to 20 minutes, the plane hits around 100 miles from the airport at exactly 1.197 minutes, 8.473 minutes, 10.857 minutes, and 18.133 minutes. So from our Desmos graph, we found that from 0 minutes to 20 minutes, we're trying to find about when does the airplane hit around or exactly 100 miles from the airport. And then from the Desmos graph, we found that it hits the 100-mile point at exactly 1.197 minutes, 8.473 minutes, 10.857 minutes, and 18.133 minutes. And then that's our answer right there.